In section 5.1, we'll finally see that all the time we spent studying the simple linear homogeneous systems in chapter 3 was not wasted. It's useful for analyzing the equilibrium points of more general systems, such as here's a system of two autonomous equations. Notice there's still no t on the right-hand side. If there's a t on the right-hand side, then you generally don't have equilibrium points at all. And what we want to analyze equilibrium points to see for a general problem, general nonlinear problem, if those equilibrium points are sink sources, etc. So let's consider the 2x2 system, and of course, as always, 3x3 or larger can be analyzed in a similar way. So we have a system of two nonlinear equations. These could be predator-prey problems, for example. First, let's suppose that x0, y0 is an equilibrium point. In other words, f of x0, y0 is 0 and g of x0, y0 is 0. So if you plug in, if you start at x0, y0, x prime and y prime are 0, so you stay there. We want to know what happens if you start close to it. So x0, y0 is an equilibrium point. Well, we introduce new variables. We'll kind of change the axis where u is x minus x0, v is y minus y0. And now in terms of u and v, the new variables, the equilibrium point is at 0, 0. At u equals 0, v equals 0. So by the change of variables, u is x minus x0, v is y minus y0. The left-hand side is du dt, dv dt, because the derivative of constant is 0, so dx dt just becomes du dt, dy dt becomes dv dt. On the right-hand side, you replace x by x0 plus u, and y by y0 plus v. Then in terms of u and v, we have this system where now the equilibrium point is at u equals 0, v equals 0, because it's at x equals x0, y equals y0. Now we want to approximate these two functions here, and we use the tangent plane. This is actually the linear terms in the multivariate Taylor series. That is, you're familiar with the normal Taylor series that says f of x0 plus u is f of x0 plus f prime of x0 times u plus higher order terms. And if you throw away the higher order terms, you can approximate f of x0 plus u by f of x0 plus f prime at x0 times u, and that's just the tangent line. But now in 2 dimensions, we can approximate this function f and g also by its tangent plane. This is the linear terms in the multivariate Taylor series. Should look analogous to the single variable Taylor series, f of x0, y0 plus partial of f with respect to x times u plus partial of f with respect to y times v. So we're throwing away the higher order terms. Well, if we're looking very close at the equilibrium point, we're only looking at points close to the equilibrium points, then u and v are small, so u square and v square are very small, so we can ignore those. So when u and v are small, in other words, when we're close to the equilibrium point, this is a pretty good approximation. It's actually the tangent plane, because this is a plane and it has the same x derivative and same y derivative as the original function. So we do the same thing for g. Write this using the linear terms in the multivariate Taylor series for g. And so now we have now remember that x0, y0 is an equilibrium point, so f of x0, y0 is 0, and so is g. So these two terms disappear, and you get approximately du dt, dv dt equals this matrix here, which is called the Jacobian matrix, times uv. And it's a Jacobian matrix evaluated at the equilibrium point, so it's just a constant matrix. So if you throw away the higher order terms, this is exactly a chapter 3 problem. So in terms of u and v, which are the new axis where you've translated things to where the equilibrium point's at 0, 0, u equals 0, v equals 0, this is exactly the problem we studied all through chapter 3, because these are constants. This is called the Jacobian matrix. The partial of alpha, first row is partial of alpha with respect to x, partial of alpha with respect to y. Second row is partial of g with respect to x, g with respect to y. Pretty obvious if you had a 3 by 3 system, the Jacobian matrix would be 3 by 3 and you'd have 3 unknowns and so forth, but we're going to study this. So that's why all we learned in chapter 3 is useful for more general autonomous problems near their equilibrium points, because near an equilibrium point, if you look at them through a microscope, they behave very much like a chapter 3 problem where the matrix is now the Jacobian matrix evaluated at the equilibrium point. So let's look at, we're going to look at 3 examples. The first example we looked at before, it's x prime is x squared minus y squared, y prime is xy minus 4. We first try to find equilibrium points, that is, find all points x and y such that both of these are 0. So if you start there, you'll stay there. Well, if this is 0, that means x squared is equal to y squared, which means y is plus or minus x. Well, y can't be minus x, because if y is minus x, this becomes minus x squared minus 4, which can't ever be 0. So y must be plus x, and in that case, this is x squared minus 4, and x is plus or minus 2. So x can be plus or minus 2, and y has to be the same as x. So we have two equilibrium points, minus 2, and 2, 2. And the Jacobian matrix here is partial of first function with respect to x, that's 2x. Partial of first function with respect to y, that's minus 2y. Partial of second function with respect to x, that's the constant y. Partial of second function with respect to y, that's the constant x. So there's the Jacobian at a general point xy, but we need to evaluate the Jacobian at the equilibrium point we're interested in. We got 2 equilibrium points. Let's find the Jacobian at each of them. One could be a source and the other a sink and so forth, so you have to analyze them separately. So at the equilibrium point minus 2, you just plug in x equals minus 2, y equals minus 2, and you get minus 4, plus 4, minus 2, minus 2. So we need to find the eigenvalues of this 2 by 2 matrix. Fortunately, we don't need the eigenvectors, because from chapter 3 we know that the eigenvalues tell us what type of equilibrium point it is. So near the point minus 2, this nonlinear equation here acts just like a chapter 3 problem with this matrix. So find the eigenvalues, minus 4 minus lambda, minus 2 minus lambda, minus 2 times minus 4. There's the characteristic polynomial. Use the quadratic equation to find the roots, and you get minus 3 plus or minus square root of 7i. So it's complex with a negative real part, and we know from section 3.4 that means the fact that it's complex means it's spiral. The fact that the real part's negative means it's a sink. So minus 2 is a spiral sink. Now let's analyze the other point, the other equilibrium point, 2, 2. And by the way, we don't care what the Jacobian looks like if it's not an equilibrium point. It's just at equilibrium points where the Jacobian has some meaning. So now you plug in into the general Jacobian general point xy. At the point 2, 2, x is 2, y is 2, that becomes 4 minus 4, 2, 2. And we don't really even need to find the eigenvalues of that, because we notice that that's exactly the negative of this matrix here, so it's going to have the negative of the eigenvalues. So we don't need to analyze these again. The eigenvalues are now the negative of these, which would be 3 minus or plus square root of 7i. So now 2, 2 is a spiral because it's complex, source because the real part is positive. And now let's look at the phase plane for this system. There's our system of 2 equations. And well, we already did this, but if you start at 2, 2 exactly, you'll stay there. But if you start real close to it, it spirals away, and in fact this one actually ends up spiraling into the other one. Remember, we predicted that 2, 2 would be a spiral source, minus 2 would be a spiral sink. If you start near minus 2, it does seem to be a sink, and it does seem to be spiraling a little. It's kind of hard to tell, but it certainly looks like it's a spiral sink. This is a spiral source. You start as close as you want, and you're going to get blown away unless you start exactly at that point. So that seems to agree with our predictions. Now let's try another problem. This is a problem in chapter 2, predator-prey problem. R is rabbits, F is foxes, and we notice that it looks like there's an equilibrium point that's a spiral sink there. Let's analyze this. We're going to have to do the HPG system solver. We'll have to call Rx and Fy, but here are your two right-hand sides of this predator-prey problem. Here it is with R changed to X and F changed to Y, and well, here it is. If you factor out, to find the equilibrium points, it's best to factor it. When you want to take the derivatives for the Jacobian, it's probably better not to factor it, but factor an X out of the first equation, a Y out of the second one. And remember, this can be thought of as the rate of change of rabbits, the rabbit increase rate, and the bigger Y is, the more predators there are, the smaller the rate of growth of the rabbits are, whereas the more rabbits there are, the larger the growth rate for the foxes are. So anyway, X equals 0, Y equals 0 is obviously one equilibrium point. They're both extinct, they'll stay extinct. We're not too interested in that. Another equilibrium point would be where this is 0, and that means X is 1/2. You go back and plug X equal 1/2 here, and you have 2 minus 1/3, which is 5/3, so Y has to be 5/3. So X equals 1/2, Y equals 5/3 is one equilibrium point. Another one would be if Y is 0, you go up here, and well, either X can be 0, or if Y is 0, then X would be 3. Set this to 0. So there's two equilibrium points. There's 0, 0 is another one, but we're not going to analyze that one. So this equilibrium point is where there are foxes are extinct, but the rabbits are not. This one is an equilibrium point where neither one of them is extinct, but they're in harmony with each other, just the right number of rabbits to eat. So first so now that we found the two of the equilibrium points, let's find the Jacobian, and it's easier to take the derivative after multiplying it out, so you don't have to use the product rule. So derivative first function with respect to X would be 2 minus 4/3 X minus the constant Y. Derivative of alpha with respect to Y is 0, 0 minus X, the constant minus X. Derivative of the second function with respect to X is the constant 4Y. Derivative with respect to Y is minus 2 plus 4X. So there's the Jacobian at a general point XY. We're going to look at it at both of the equilibrium points, 3, 0. Plug in X equal to 3, Y equals 0, and you get 2 minus 4, which is minus 2. That's minus 3. Y is 0, so that's 0. X is 3, so that's minus 2 plus 12 is 10. So there's the Jacobian matrix at that point. And fortunately, this one you don't need to, since it's upper triangular, you can just read the eigenvalues off the diagonal. Remember, we had a problem in chapter 3 that showed that upper triangular or lower triangular matrix, the eigenvalues are just minus 2 and 10. After all, if you wrote the determinant of j minus lambda, it'd be minus 2 minus lambda times 10 minus lambda, and then you have 0, so you basically already got it factored as minus 2 and 10. So the eigenvalues are minus 2 and 10. One's positive, one negative. They're both real. That means it's a saddle point. Okay, then the other equilibrium point's a more interesting one, a little harder to analyze. You take the general Jacobian, plug in X equal to 1/2, Y equals 5/3, and you get this. You can't just read off the eigenvalues off the diagonal because that's not upper or lower triangular, unfortunately. So you calculate them the hard way: minus 1/3 minus lambda times 0 minus lambda minus a minus 1/2 times 20/3 comes out to be this. Use the quadratic equation, and the eigenvalues are minus 1/6 plus or minus square root of 119 over 6i. So it's complex, therefore it spirals, negative real part, spiral sink, which agrees with what we saw in that picture, but let's do it ourselves. Okay, here's the predator-prey problem. We have an equilibrium point at 1/2, 5/3. Start most anywhere, and it spirals in to that equilibrium point where foxes and rabbits are in harmony with each other. The other equilibrium point was 3, 0, which is around here somewhere, and it's a saddle, which means it's part source, part sink, but mostly source, as we saw. And it looks like pretty much anywhere you start, it gets blown away. But if you start with no foxes, start exactly on the x-axis, let's see what happens. Let's try x is 2.5 and no foxes. Then it actually does converge to, well, here we started at 2.5 rabbits, no foxes, ended up with 3 rabbits, no foxes. The limit of 3 is basically you run out of, farmer runs out of lettuce, so there's a limit to how many rabbits can be. Even without any foxes, there's a limit to how many rabbits according to that model. So the, let's see, 1, 0 must be the eigenvector for the negative eigenvalue, minus 2 in this one. The third problem is one we've actually seen many times before. It's the damped spring problem. This one's actually linear, so it's a chapter 3 problem. We don't have to approximate it by chapter 3 problem. It is a chapter 3 problem, but we can still analyze it. Now we have to use x and y as the variables, so x will be the displacement of the spring mass from equilibrium, y will be the velocity. So the first equation just defines the velocity to be yx prime, and the second equation, we're assuming the mass is 1 to keep things simple here. So this is the acceleration, the derivative of the velocity, the second derivative of the position, and that's minus k times the position minus b times the velocity. So the Jacobian of this, derivative with respect to x is 0, with respect to y is 1, derivative with respect to x is minus k, with respect to y is minus b, and that's just a constant matrix. So at the equilibrium point, the only equilibrium point is 0, 0. That's where there's 0, where it's the spring is at rest. It's 0 position and 0 velocity. That will make both of these 0. At that point, and at any other point, because there's no x or y in there, so the Jacobian at any point is this matrix. So we calculate the eigenvalues as 0 minus lambda minus b lambda minus lambda minus a minus k times 1. We get lambda squared plus b lambda plus k, which should be very familiar. And the eigenvalues then are minus b over 2 plus or minus the square root of b squared minus 4k over 2. Now, if b squared is bigger than 4k, we're assuming b is positive, of course. It's the frictional coefficient. Can't be negative. If b squared is bigger than 4k, then you'll have 2 real roots, but they'll both be negative because the square root of b squared minus something is less than b. So it's minus b over 2 plus or minus something smaller than b over 2. So there's 2 negative eigenvalues, which means 0, 0 is a sink, which means you'll go directly there without spiraling, without oscillating. On the other hand, if the frictional coefficient is less than 4k, so if there's a whole lot of friction, it'll just die down immediately. If b squared is less than 4k, there's friction but not as much, then you have this is negative, and you have complex eigenvalues, but the real parts are negative, so it's a spiral sink. Well, that's assuming B is positive, which it has to be. If B were negative, well then in the first case you'll have two positive roots. In the second case you'll have complex roots with a positive real part. In other words, you'll have source and spiral source, but of course that's impossible. That would negative frictional coefficients impossible. That would violate the second law of thermodynamics. Okay, here's the damp spring problem. Now K we're taking to be 1 and B will be 3, so B squared is bigger than 4K, so it has a high frictional coefficient. It should just die down without oscillating. If we start most anywhere, if you start here, that means you just pull it up that distance and let go. There's zero velocity at the initial point, and the X, which is the height of the spring, just dies down. It doesn't oscillate. On the other hand, if we change this B to say 1, then B squared minus 4K is negative, so now it should oscillate as it dies down. Let's make it even smaller to make it oscillate more. So let's say small frictional coefficient. And start about the pull it up and let go. And as you can see, it oscillates. This is the actual spring. This is the velocity, so there's enough friction to make it die down, but it not so much that it goes straight there. Okay, one more example. This is mentioned in the book. It's called the van der Poel's equation, and it's just to illustrate some strange things can happen. When we analyze an equilibrium point, that only tells us what happens near the equilibrium point. It doesn't tell us what happens if it's blown away. And one equilibrium point for this is 0, 0, obviously, and it is a spiral source. If you start close to there, it spirals out, but the interesting thing is once it gets out here, it just goes through this same funny looking loop over and over. It basically converges to a loop, and it's not even a circle. So strange things can happen out here, but if you analyze this point here, you can show that it's a spiral source. What happens when you get away from the source? That linear approximation is not any good anymore, so you can't predict. Whereas the real chapter 3 problems, they have the same form no matter where you start. So if they're spiral sink, they'll spiral in to the origin no matter where you start. If it's spiral source, it'll spiral out to infinity no matter where you start. But with nonlinear problems, all we can say is what happens if you start close to the equilibrium point.